In this video, I'm going to show how to draw Kaplan-Meier plots using SPSS. And dataset we use is cabbage.sav, and this dataset contains data from a VA RCT comparing effect of cabbage versus standard medical therapy among patients with stable angina pectoris. Primary study endpoint is all-cause mortality at 6 years. Coded 1 for deceased and 0 for alive. And time variable is a time to death within 6 years. The variable name is serve year 6. Okay, so the data set cabbage contains 686 patients, okay, and about half of them are randomized to cabbage, and the rest are randomized to standard of medical therapy. And these two are outcome variables, and this is the exposure of interest. So 1 is coded for cabbage and 0 is coded for standard of medical therapy. So to do Kaplan-Meier graph, you go to Analyze, Survival, and Kaplan-Meier. Here is a dialog for Kaplan-Meier. You put the serve year 6 to time box and status 6 to status box. You need to let SPSS know what coding system you use for events. So I put the 1 for deceased patient. And treatment variable, cabbage versus medical therapy, and you put under factor. And then click option. And if you want to draw a graph where y-axis is survival, cumulative probability of survival, and you click this one. Or if you want to show y-axis being cumulative probability of death, then you put 1 minus survival and click continue. And if you want to go ahead to compute p-value to compare cabbage versus medical treatment, and click compare factor. And there are 3 tests and you can choose from, and a typical choice would be a log rank test. And click continue and OK. And SPSS produced big table and showing cumulative probability of survival at each time points. So here, and you know, at the time point 0.19 years after randomization, and there are 353 patients left in risk. So when you scroll down, and you see at 5.936 years after randomization, and there are 258 patients left in the cohort of medical therapy, and cumulative probability of survival is 0.729. And you can see the same thing for surgical group, cabbage group. Okay. So if you scroll down, and at 6 years, they have 261 patients left in the risk set, and cumulative probability of survival is 0.786. Okay. And when you graphically show this cumulative probability of survival, and this is a graph. So blue line shows cumulative probability of survival for medically treated group, and green line is for a cabbage group. So you can see survival of cabbage patients are higher, better than medically treated patient. And although early time point, and you see the cabbage patient has higher mortality. So this probably due to high operation mortality involved with cabbage. And this tick mark indicate when the censoring occur. So this study has extremely good follow-up time. So no one in fact was censored within 6 years. So you had a tick mark at the very end of the follow-up. Okay. And this is 1 minus cumulative survival, which is cumulative probability of death. So you could choose to plot this graph in your paper instead of the survival graph. For Kaplan-Meier graph, it is always better to put the number at risk for each group. for each tick mark used in x-axis. So here I plot the tick mark for every year after randomization. So and you can see the beginning, we have 354 patients in the medical group and 332 patients in the surgical group. And then at 1 year, it reduced to, medical group reduced to 330 patients, and the surgical group reduced to 307 patients. And at end of 6 years, and there are 258 patients left in the medical group and 261 patients left in the surgical group. And it is very important to put the number at risk, because when you have a small number at risk, and then the large drop in Kaplan-Meier curve is due to loss of patients from risk set instead of many events occur at that time point. So to differentiate, and it is always better to put p-value in the graph so that reader does not have to look the p-value in the footnote or in the text. Unfortunately, SPSS does not produce number at risk automatically, so you need to edit this graph by hand and grabbing these numbers and from the big table. So this is the big table we have on the output, and to get number at risk at 1 year, and what you do is you go to the time point and right before 1 year mark. So we don't really have exact number of 1.000, so you go to a time of 0.912 year and then use a number at risk and find a number at risk for this time point, and this number is for medical group. You put this number in the graph by hand. So what I usually do is you go to SPSS, okay, and you edit the graph as much as you can. In the early version of SPSS, and you could copy and paste in the PowerPoint, and then you can edit there easily. But this version I haven't found a way to edit in PowerPoint. So let's edit as much as possible within SPSS. So you double click and go to chart editor, and if you don't want like blue background, and then you can click white background, okay, and then make background white. And if you want to put the beta label here, okay, and popular choice for the label is percent survival, okay, and let's get rid of this survival function title. So you highlight and delete. Okay, and then I like to put label by hand after I copy this graph into PowerPoint. So let's delete. There's no delete button. Let's delete. You highlight this, okay, and right button, delete. Okay, and I don't want decimals on x-axis, so let's delete zeros. I don't want zeros after decimal point, so let's delete zeros. In order to delete zeros, you click number format and put 0 in the decimal places and apply. Okay, and I think we're ready to paste copy and paste this graph on the PowerPoint. So you go to you actually have to get out of a chart editor, okay, and then now you copy and then go to PowerPoint. Let's create a new page, and I'm going to place this graph in the PowerPoint. Okay, so now you put number at risk, and right, and surgical, and you just type these numbers, find the numbers for year 1, 2, 3, 4, 5, 6, and type them by hand. And that's how you can edit Kaplan-Meier graph. And if you use other software such as R or Stata, there is an option you can automatically put number at risk under each tick marks for each group. So let's look at Spss output. And under this big table, okay, and there is a table showing mean survival time and median survival time. And mean survival time for medical group is 5.92 years, and mean survival time for surgical group is 5.26 years. And SPSS can compute confidence interval for each mean survival time. And as you see, there are no median time of survival. And because these Kaplan-Meier plots does not cross 50% line, okay, so follow-up is not long enough to observe cumulative survival go below 50%. So median survival time is NA here. Okay. And overall comparisons in this table gives p-value for log rank test. So p-value is 0.091. So we did not see statistical significance on the difference in two survival curves. And there are two other tests available in SPSS, and Bresdell test, okay, or Tyrone-Ware test. Log rank test works well when you have these patterns in survival curve. So the y-axis. Log rank test works well when you have two survival curves with this pattern, and it also works well with this pattern, and I explain more. And this pattern indicate risk is not really changing over time, and so therefore the ratio between two risks are constant over time. Okay. And this pattern indicate risk is changing over time. Okay. So you have moderate risk here, and then risk is accelerating here, and then got stabilized. And hazard change, risk change over time, although if you see the ratio between two risk, and ratio seems constant. So in this case, log rank test works well. And Bresdell test works well. You have early difference. Okay. Larger difference at early time point. And when the Kaplan-Meier curves cross over, and neither test works. Neither test works. Okay. And we will talk more on this in the Cox regression lecture. But when the two survival curve cross over, and it is better to look at risk, effect of your exposure differently for each interval. So here you see the surgery is not working, but here the surgery is working. So we chose to use log rank test, and p-value is 0.091, and which indicate that there was no significant difference in survivorship between medically and surgically treated patient during 6 years of follow-up. Look at the scenario 1. You want to compare 3 groups or more with log rank test. Okay. And next example, we are going to compare mortality among 3 groups defined by clinical risk. So 1 indicate mild risk group, and 2 indicate moderate risk, and 3 is a severe risk group. And we want to compare mortality among these 3 groups. So you go to analyze again, and survival and Kaplan-Meier, and instead of treatment, and we have a clinical risk here. Okay, and let's So we keep same option. We don't need all. We keep the same option. Pick the log rank. Okay, continue. And option, we want to show survival. In this case, I'm not showing cumulative mortality over time. Okay, and let's disable big survival table. Okay, and click continue and OK. Alright, so now you have three curves. Okay, so blue is for mild, and green is for moderate, and gray line is for severe risk group. And when you look at p-value, and log-rank test give you one p-value. So what does this mean? You have multiple groups, more than two groups, and you have one p-value. So this is the same idea as ANOVA test. So the null hypothesis for this log-rank test is whether three survivorship functions are the same or not. And so we rejected it, and that means at least one group's survivorship function or survival is different from another group. So we now are allowed to look at each pairwise. And so let's do pairwise comparison. So you go back to Kaplan-Meier graph again. Kaplan-Meier again. And now click on options. Now click on compare factor. Okay? And in order to do pairwise, and you click this button, pairwise over strata. Okay? And continue and OK. Okay. So now you have this table, pairwise comparisons. So as you see, there are 1, 2, 3, 4, 5, 6 p-values. And although you have a redundance, so here 0.008 the same here, 0.000 the same here, and 0.013 the same here. So you actually do have three pairwise, three p-values here. So when you compare low risk versus this p-value, compare moderate risk group versus low risk, and this p-value compare high risk group versus low risk, and this p-value compare high risk versus moderate risk. Okay, and okay. And since you have three p-values, so although the overall test rejected, and we are allowed to look at each pairwise, and we probably don't need to adjust for Bonferroni or multiplicity, although there is a risk, and reviewer might tell you you have to adjust for Bonferroni. And in order to avoid that, so let's see if we can do trend test. And so do you see dose response relationship? The higher the risk category, okay, and the higher the mortality is. I think that seems true in this case. So if you want to do linear trend test, and you go to survival, Kaplan-Meier again, and go back to compare factor, and then now you click on this button, okay, and linear trend for factor levels. Okay, and then make sure you click pulled over strata as well, and continue and OK. Alright, so now the log rank provides just one p-value, so this is a trend test. So this p-value indicates the greater the risk category is and the higher the mortality. In the last several slides, I'm going to show you how to truncate survival curve. And when you collect data, and we don't directly collect the data on duration of follow-up. Instead, and we collect the data on date of randomization or date of study entry, and then we have data on date of death or date that patient were last seen. And then to perform survival analysis, and we do calculate duration of follow-up by subtracting date of randomization or date of study entry from date of event or date of last seen. And therefore, for patient who came to study early on and you have a longer duration, although for patient who came to your study later time and you have a shorter duration. So if you don't truncate survival time and plot the Kaplan-Meier plot, you end up having these problems. So let's look at this Kaplan-Meier graph. And in the blue line, and you have a relatively large drop in here and here. And that doesn't mean you have many deaths, many events occur just at these 2 time points. Instead, and you start losing patient, so these tick marks indicate patient being censored, and therefore you only have few patients left in your study and after 20 months follow-up, for example. And so if you have only 4 patients left and 1 event contribute to 25% drop in Kaplan-Meier graph. If you have only 2 patients left in your cohort and you have 50% drop, 1 event contribute to 50% drop in Kaplan-Meier graph. Okay, so therefore, we can't really trust data Kaplan-Meier estimate when data are too sparse. Okay, you have very few number left in your study, and therefore it is advisable to truncate survival curve at the time point where you relatively have a large number of patients left in your study and also a really clinically relevant duration of follow-up to answer your study question. So in this study, and I asked my collaborator, and for how long is the durations we should be looking for death among patients in ICU and to measure effect of delirium. Okay? And how long do you think delirium should impact on patient death? And my collaborator said, well, probably 6 months. So instead of looking at data, we apply or we chose 6 months, and we truncated survival curve at 6 months. Okay? And so I'm going to show you how to truncate survival time. Now, example we have, instead of this data set, and we are going to use our lecture example of cabbage. This data set is from our lecture. We examine effect of cabbage, which is a treatment variable, 1 for cabbage, 0 for medically treated patient, on the patient survival. And what we use in the class is survival up to 6 years. Although this study is a long cohort study, so patients were followed up to 23 years. Okay. So, for example, this patient have a duration as long as 22.3 years. So what I did for this lecture is I truncated this survival time at 6 years. Okay. And so our analysis focus on effect of first 6 years. So I'm going to show how to create these 2 variables. So status 6 is a binary death and alive variable at 6 years, and based on this original status, which reflect survival at 23 years. And the new survival time is truncated at 6 years, and that this reflect what happened to each patient at 6 years based on original time variable for 23 years. So let's start creating new time variable, survival time truncated at 6 years. And for patient in whose survival time is greater than 6 years, and we replace time to 6. So this is a new variable, serve year 6, and we put the 6 here, and if serve year is greater than 6. Okay, so let's check, right? So now, yes, these values are converted to 6. And next one, for the patient in whose survival time is less than 6, and we simply copy original value. So go to serve year 6 and put serve year. Okay, and if serve year is less than or equal to 6. Right, so we're done with creating new time variable. And next one, we create new status variable truncated at 6 years. And to do that, for people who have survival time longer than 6 years, we code status to 0 because they're all alive at 6 years. Okay? And we do that. Right? And for patient and whose survival time is less than 6 years, okay, and we copy the value of status to a new variable. So to do this, so the simplest way to do this is you go to compute variable and then create a new variable, so status 6, okay, and then assign 0 for everybody. Okay, so we disable this optional case selection condition, right? And make sure you have include all cases selected, and then click OK. So now everybody got the value of 0, right? So what we are going to do next is for patient whose survival year is less than 6, we will copy this status variable. So person who is censored, and we put 0, and person who died before 6 years, and we put 1 here. So we go back, right, and then change this to status, okay, and if serve year is less than 6, right. So you go to the data set and then person who died before 6 years, and now you have 1 and on this new variable. Okay, and after you do that, and let's make sure we redo Kaplan-Meier graph, and we have similar looking Kaplan-Meier graph. Yes, it does look similar to what we had in the lecture note. Right? So in this way, and we can eliminate to analyze data and where the follow-up is too long for its clinical relevance, and also data are too sparse because we have fewer patients left in the risk set.